Good day to you, dear colleagues and participants of the 8th International Conference on Fracture, Fatigue and Wear. My name is Vitalii Peshko, and I would like to present you a report on a scientific research estimation of steam turbine shafts fatigue damage caused by torsional vibrations. The authors of this work are Olga Chernousenko, Anatolii Bovsunovsky, Vitalii Peshko, and Bogdan Marisyuk. So, let's talk a few words about the relevance of this research. In the world energy sector, cases of brittle destruction of turbine units due to the fatigue damage are rare. However, they lead to catastrophic consequences with the significant material losses. The fatigue damage of steam turbine rotating elements during operation is dependent on the dynamic regimes of loading, which can cause transverse and torsional vibrations of the shaft. A lot of investigations were devoted to transverse vibrations of turbine shafts. At the same time, torsional vibrations are insufficiently studied. In general case, the reasons of turbine shafts' torsional vibrations can be the reactive torque that occurs due to a short circuit on generator, short circuit in power lines, connection of generator to power network with insufficient synchronization, touching of rotating parts to the turbine shell, and all possible electromagnetic effects on generator. As a result, the magnitude of the reactive torque can be by several times bigger than the magnitude of the torque at stationary regime of turbine operation. The accumulation of fatigue damage in turbine rotating elements can be attributed to the frequent startups, which are usual even for thermal power plants. The estimated number of such launches during the operation time of turbine units is nearly 2000. At each startup, at least one networking of turbine and generator happens. The short-term reactive electromagnetic shaft torque arises by reason of the difference of the phase shift angle between the vector of turbine generator electromotive force and the vector of power network voltage. Thus, torsional vibrations of turbine shafts occur due to this reactive torque. In some cases, the intensity of torsional vibrations is high enough to be the reason of fatigue damage. The number of cycles of vibrations with maximal stress amplitude exceeding the fatigue limit of rotor steel at each startup of turbine can be in the range from tens to thousands. As a consequence, during the lifetime of turbine operation, fatigue damage gradually accumulates. The object under investigation was steam turbine K200. Turbine of this type consists of three rotors: high pressure, middle pressure, low pressure, and generator. The geometric model of the shaft is developed in accordance with the drawings of the manufacturer and takes into account the main structural rotating elements of the turbine. At the same time, the geometric design of the blades and bandage connections was replaced by toroidal discs to reduce the time of numerical calculation. The size of these discs are specially selected in such a way that their mass is equal to the mass of all blades and its mounties of this stage. Also, the outer diameter of the torus corresponds to the similar diameter of the blades. The studies conducted by the authors showed that such replacement is justified, since the error is about 5%, but the calculation term is reduced significantly. The model consisted of 200,000 finite elements. The shaft is loaded by three static torques, caused by the pressure of steam. Torsional vibrations are excited by the reactive torque, which can be of electromagnetic or mechanical nature. Total static torque is the sum of static torques acting on rotors. The reactive torque was assumed to be a P-shaped function with short duration, which can simulate unsuccessful connection of generator to power network or mechanical interaction of turbine structural elements with the turbine shell. Its amplitude was related to the static torque in the following way. So, on this slide we can see generator power dependence of damping characteristic of four modes of turbine shaft torsional vibration. Damping characteristics of shaft was experimentally determined for different mode of shapes in this walk. In calculations, damping in terms of logarithmic decrement were accepted in this way. The first phase of this research is calculation of shaft stress-strain state during turbine operation at rated load of 200 MW. The values of torque on rotors were assumed to be 200 kN for high pressure rotor, 290 kN for middle pressure rotor, and 160 kN for low pressure. The sum of these moments is a nominal static torque, acting in the area of coupling between the shaft of steam turbine and the generator. This figure demonstrates equivalent stresses by Mises in the stationary mode of operation of K200 steam turbine. As can be seen, the highest stresses are observed between the low pressure rotor and turbine generator. They are in the range of 150-180 megapascals. The stresses that occur in the area of semi-rigid coupling between the middle and low pressure rotors are nearly 70 megapascals, and in the area between the high and middle pressure rotors are nearly 50 megapascals. The obtained stresses do not exceed the strength limit for 25 chromium steel, so the stationary operation does not lead to the significant accumulation of damage in the turbine shaft. On the next phase, the stress-strain states of the shaft were calculated for the forced vibrations caused by the short-term reactive torque, and then for the free vibrations when the reactive torque disappears. As it was mentioned above, the reactive torque was accepted to be 3 times bigger than the static torque. The duration of reactive torque was chosen so that the intensity of torsional vibrations was the highest, namely 20 milliseconds. The most dangerous areas of the turbine shaft are coupling between high pressure and middle pressure rotors, as well as the sections between middle and low pressure rotors and between low pressure rotor and turbine generator. These figures demonstrate the time dependence of equivalent stresses amplitudes for these areas as a result of the action of the reactive torque. The maximal amplitude of equivalent stresses between high and middle pressure rotors is observed after 71 milliseconds from the beginning of the reactive torque and reaches 550 megapascals. The maximal stress amplitude between middle and low pressure rotors is observed in the fourth cycle of vibration at about the same time and reaches 495 megapascals. Equivalent stress amplitude between low pressure rotor and turbine generator reaches their maximal value after 16 milliseconds after the arising of torque and reaches 800 megapascals. This value somewhat exceeds the strength limit of rotor steel. Approximately in 4 seconds after cessation of the reactive torque, the vibrations completely dump. Now let's estimate an effect of reactive torque on fatigue damage of shaft. The fatigue damage of the shaft in its most stressed areas was estimated with the usage of the Palmgren-Miner hypothesis. This variable is the number of cycles with stress amplitude which exceeds the fatigue limit of rotor steel, and this one is the ultimate number of cycles till destruction. Calculations of fatigue damage of the shaft was calculated with the usage of the fatigue curve of the rotor steel 25 chromium from this walk. The experiment was carried out at a symmetric loading cycle and temperature of 20 Celsius degrees. The effect of high temperature, escape factor, and asymmetry of loading on the fatigue characteristics of rotor steel was taken into consideration by means of experimental coefficients. Euler diagram in this case has this appearance. This variable is the amplitude of cyclic stress. There are few constants values. N is the number of cycles, and there are scale coefficient, asymmetry, and temperature coefficients. Scale and temperature coefficients were taken from this experimental study, and the asymmetry coefficient was calculated with this equation from this paper. The turbine shaft fatigue damage, which is accumulated during operating time, was calculated as a result of 2000 actions of the reactive torque. It is necessary to note that the failure takes place in the case of damage equal to 1. The estimation of fatigue damage was based on the supposition that the reactive torque lasting is distributed uniformly in this range of time. The averaged over this range fatigue damage was calculated according to the following equation. So, on this figure we can see number of net walk-ins, dependencies on the averaged fatigue damage of turbine shaft in the area between high and middle pressure rotors, and between middle and low pressure rotors. The exhaustion of the turbine resource due to the fatigue damage to the shaft occurs in 1536 actions of the reactive torque in the area between high and middle pressure rotors, and in 1263 actions of the reactive torque in the area between middle and low pressure. Also, it should be noted that the amount estimation of fatigue damage is somewhat simplified, since it suggests that all 2000 actions of the reactive torque have the same parameters. Of course, real scenarios of loading are much more complex. The developed procedure can be applied for the evaluation of turbine shaft fatigue damage if the parameters of the reactive torque will be measured in operation of turbine units. And finally, let's highlight some conclusions of this research. Long-term exploitations of turbine equipment of thermal power stations, which undergo into frequent startups and shutdowns, gradually accumulates fatigue damage in the most stressed areas of turbine shaft. The reason of fatigue damage is the intensive transverse or torsional vibrations of the turbine rotating elements of different nature. The experimentally analytical procedure to estimate the fatigue damage of turbine rotors because of torsional vibration was developed. To apply this procedure in practice, it is needed to know the intensity of turbine shaft torsional vibration in operation of turbine unit. For the reactive moment with the parameters which were assigned as an example to show the idea of the procedure, the most stressed area of the turbine shaft is the area between low pressure rotor and turbine generator. The least stressed area is the area between middle and low pressure rotors. In any case, under the action of the reactive moment with the chosen parameters, the resource of turbine unit substantially drops. In general case, the intensity of turbine shaft torsional vibrations is dependent on the magnitude, duration, and the shape of the reactive moment time function. Thank you for your attention.